Hi, welcome again to the series in which I'm creating a 4-bit computer and digital logic simulator. In the last video, we created some of the basic units of memory and computation. That was a full adder and a 4-bit register. So today we're going to be expanding on these concepts to bring about some of the more complex chips that may be more familiar to us. For your convenience going forward with the series, I'll try to split the video into chapters based on what chip we're working on. Firstly, I would like to work on building the random access memory, or RAM for short. RAM stores a list of instructions for our computer to follow and allows us to write programs in assembly. With a 4-bit computer, RAM is rather limited, storing only 16 bytes at a time, and each byte can just be stored by a register. The first issue with the current register I'd like to fix is the fact that they're always outputting their value, and I'd like to be able to tell them whether or not we actually want to read from that value, because sometimes that might interfere with other processes. Using AND gates, we can specify a read pin to tell whether the information is being used or not. I'll unimaginably call this unit a complex register, or CPX Register for short. Unfortunately, there is no better way to do the next part. It is ridiculously tedious. In order to tell which register I want to use, I need to convert binary numbers into decimal values. This requires a series of NOT and buffer gates for each number from 0 to 15. I decided to take the worst possible route and make 16 separate chips for each number. Couldn't you just make like a chip for 2-bit numbers and then use 2 of them to select from an array of registers? Yeah, you could. Now if you link these units up in the right way, you should get a gate that will just convert any binary number right to decimal. Really useful. I don't know my computer logic very well, but what I do know is that I need to have a sort of OR gate that works for entire bytes of information. So I came up with a pretty cool name for it. A BYTER. Isn't that neat? Well, I figured I'd use it a lot and it'd be pretty big, so yeah. Okay, so now it's time to work on a section of the RAM. So the RAM will come in 4 parts, and it's pretty simple. Each part will have 4 registers, which will total 16 registers, and I can just put that data together through the byters in order to get one signal at the end, and then using AND gates I can decide which memory addresses to use. So now I can just connect all these smaller RAM modules together, and I can use the binary to decimal converter in order to specify the memory address for each register. Alright, so the next part here is going to require a lot of maths. So I'm going to cover that real quick. So this is a wonderful segue into my MS Paint explanation of 2's complement and negative numbers in binary. Alright, subtracting numbers in binary, that's the first thing we need to know. How does that work? Well, it uses something called 2's complement. So if you have a number in binary, like 6 for instance, MS Paint doesn't want to cooperate. Alright, you have, like, for instance, the number 6 in binary, and you want to subtract 2. Okay, now, if you have the number 6 in binary, and you want to subtract 2, you know you should get 4. But how do you subtract 2 from 6? How do you subtract when we don't have a full subtractor? Well, here's the fun thing. We already made a full subtractor in the last video. But how? Well, that's the interesting thing. Because a full adder is also a full subtractor. We just need to be able to add a negative number. So how do you make a number negative? That is using 2's complement. So 2's complement is kind of weird, a little funky, and just a bit wacky. So that's 6 and that's 2. And so basically, to subtract them, this has to be a negative number. And so, to create a negative number according to 2's complement, we need to invert the number. So basically every 0 is a 1 and every 1's a 0. We also need to add 1. So just add 1. And now we just add these together, we will get 4. So that's is basically subtracting numbers with a full adder. So yeah, another interesting thing is if you are subtracting and you get a carry in your number, it means that you have a negative number. So for instance, we could use some sort of logic so that if you have a carry and you are subtracting, which can just be done with an AND gate, then we know that it's negative, and so we can light up a flag that says it's negative, which can then be one of the outputs on our ALU when we make it. And if it's just a carry, then we know it's got a carry. Right? That's pretty simple. And in order to make sure we don't get these confused, for instance, if there's a carry and it's subtracting, we don't want to show both negative and carry, we just want to show negative. So in order to do that, what we need to do is just use an AND gate again. But first, we want to make sure that we are not subtracting. So we would then just use a NOT gate and an AND gate, and we would know whether or not our carry is actually there or not. And so essentially this process can be used to subtract.
Now if you connect 3 4-bit adders like this, then you can create a multiplier, and this obviously multiplies numbers. Now it becomes necessary to build some sort of module that can do all of this math in one, and that module is called the ALU, or Arithmetic Logic Unit. Combining a 4-bit multiplier and a 4-bit adder like so can create the main part of our ALU, which just adds and multiplies 4-bit numbers. Adding XOR gates between input B and subtract will invert input B if subtract is on, which does the first step in 2's complement. Now, this rather complicated set of gates helps the computer decide which flags to use. While there's probably better ways to do this, I decided to just add the subtract signal to the inverse of input B, and this finishes off 2's complement. And finally, the ALU can be completed with this little set of logic gates to just decide how to operate the carry and negative flags, as we discussed earlier. Now, one final part that maybe should just be in the next video is the program counter. And this is just a special register that is going to count up from 0 to 15 so that we can assign an instruction to everything to, make the computer do stuff. The counter should basically just be a register that is feeding into an adder that feeds right back into the register, and just counts up every clock pulse. It also will be necessary to have an ability to set which step to be on. So that's what the 4-bit input on top is, as well as the third 1-bit input. That's called the jump signal. Anyways, you have now made it to the end of the video. I don't know what else to say. In the next video, we're going to be doing something I'm not sure how to do yet, so the next video might take a long time, but basically we're going to be making the control unit, which a lot of people don't seem to want to share how a control unit works. So this is going to be quite difficult because it's a hard thing to do. But basically it's going to interpret instructions, be able to tell whether it's an instruction or a number or like what to do, you know, and like it's gonna be crazy, but we're gonna figure it out. Now if you connect now if you connect 4
No, not making 8